When you picture science, what comes to mind? For many of us, it's this steady, relentless climb, like scientists are tirelessly adding bricks of knowledge one by one to a grand, ever-expanding building. It feels so reassuringly linear, doesn't it? A constant accumulation of truth. But what if that common picture, the one often reinforced by our textbooks, is, well, fundamentally misleading? What if the history of science isn't a gradual build at all, but something much more dynamic, disruptive, and at times even revolutionary?
That's precisely the radical challenge. It's right at the heart of today's deep dive, Thomas Kuhn's groundbreaking work, The Structure of Scientific Revolutions. This book, well, it fundamentally reshaped how we understand the very nature of scientific progress.
Okay, so our mission today is to unpack Kuhn's central, maybe revolutionary ideas. We're going to explore how science really progresses, not just by adding facts, but through these dramatic, sometimes jarring shifts in understanding. And we'll dig into what that means for how scientists, and perhaps even you listening, perceive the world around them. Time to dive in. So let's start by questioning that conventional image of science. As you said, the way textbooks often portray scientific knowledge is this smooth, linear path. It's almost as if every scientist through history was perfectly aligned, striving directly for the current theories and models we hold today.
Right. It's an understandable simplification, maybe, for teaching. But it completely misses the messy human reality of scientific advancement. Kuhn's own journey to this profound insight is a fascinating story in itself. He actually began his academic path as a theoretical physics graduate student, quite close to finishing his dissertation.
Oh, really? Physics?
Yeah. But then, what he called a fortunate involvement with an experimental college course on the history of science. Well, it utterly radically undermined his basic conceptions about how science worked and why it succeeded. He realized that exposure to out-of-date scientific theory and practice, old science, just didn't fit the neat, cumulative enterprise he thought science was. This disjunction was so significant it led to a drastic shift in his career, moving him from physics to the history of science, and then gradually back to the philosophical questions that initially drew him to history. Imagine being that close to a physics PhD and then changing everything.
Wow, that's a huge pivot from the hard sciences right into the philosophy of science. And he wasn't doing this in isolation, I gather. His thought was profoundly influenced by scholars like Alexandre Koyré, Emil Meyerson, Helene Metzger, and Elise Meyer, people who showed what it was really like to think scientifically in very different historical periods.
Absolutely. And he also credits psychologists like Jean Piaget, philosophers like Benjamin Lee Whorf, and W.V.O. Quine, and Ludwig Fleck, whose work apparently made him realize his ideas might need to be set within the sociology of the scientific community itself. It wasn't just about ideas, but about communities.
It sounds like a journey of intellectual upheaval in itself. And his early lectures, like The Quest for Physical Theory back in 1951, that was his first chance to sort of test these developing, almost heretical notions out in public.
That's right. Testing the waters, so to speak.
So if that's Kuhn's background and his foundational challenge to the linear view, how does he then describe the everyday work of science? He introduces this central concept he calls normal science, doesn't he?
He does. He defines normal science as, let me get this right, research firmly based upon one or more past scientific achievements which a particular community acknowledges for a time as supplying the foundation for its further practice. These are the classics, the things you find in textbooks, illustrating successful applications, providing a framework.
Okay, the foundations.
And these foundational achievements, which Kuhn terms paradigms, share two key characteristics. First, they were sufficiently unprecedented to attract an enduring group of adherents away from other competing scientific activities. They had to be compelling. Second, and this is crucial, they were sufficiently open-ended to leave all sorts of problems for practitioners to resolve. Think of monumental works like Newton's Principia, Franklin's electricity, or Lavoisier's chemistry. They don't just solve problems, they define what the field's problems are.
Right, they set the agenda.
And this stands in stark contrast to what Kuhn describes as the pre-paradigm period. Take physical optics before Newton, or electricity before Franklin. In those eras, there was no single generally accepted view. Instead, you had competing schools and sub-schools, each trying to build their field anew, often emphasizing phenomena their own theories explain best.
Sounds messy.
Very. The dialogue among them was often directed as much to the members of other schools as it was to nature. It sounds like a rather chaotic and maybe often unproductive way to do science.
And the emergence of a paradigm really changes the game then. It leads to a more rigid definition of the scientific group. Once the paradigm is in place, scientists can then concentrate exclusively upon the subtlest and most esoteric aspects of their field. It also profoundly changes how research is communicated, right? No longer works aimed at the general public like Franklin's book.
Exactly. Instead, research appears as brief articles addressed only to professional colleagues who all share that common paradigm. It becomes much more specialized, more internal. It's a closed shop in a way.
This brings us to a fascinating analogy Kuhn uses. He describes normal science as puzzle solving. Now, this begs the question. Why would scientists undertake problems when the outcome, or at least the type of outcome, is often known in advance? It doesn't sound like radical discovery.
And it isn't, not in the sense of aiming for major novelties. The motivation for the individual scientist isn't necessarily to discover something entirely new and unexpected. It's more to add to the scope and precision with which the paradigm can be applied. The real challenge, the puzzle, is in achieving the anticipated in a new way, proving one's skill as an expert puzzle solver.
Ah, okay. Like a jigsaw puzzle.
Exactly like a jigsaw puzzle. You know what the finished picture will generally look like? The paradigm guarantees that, but the method to get there still requires ingenuity, skill, persistence.
That's a crucial distinction. It means real scientific progress, for Kuhn, isn't always about the radical eureka moment we often imagine. It's often about the painstaking, meticulous work within an accepted framework. And paradoxically, it's that very precision that sets the stage for future revolutions.
Precisely. And these puzzles in normal science are governed by rules, as Kuhn calls them. These can be explicit scientific laws, like Newton's laws, Boyle's law, Coulomb's law, the obvious stuff. They also include instrumental commitments. The accepted use of a spectrometer, for instance, implicitly defines certain procedures and expected results, and even quasi-metaphysical commitments play a role, like the 17th century belief that the universe was composed of microscopic corpuscles. That led chemists like Boyle to focus on reactions they saw as transmutations because they displayed corpuscular rearrangement. It shaped their questions.
But here's where it gets really interesting, because Kuhn has a more nuanced view, right?
Right.
He suggests that scientists actually learn and practice not just through explicit rules, but through models acquired through education and shared examples. He even draws a parallel to Ludwig Wittgenstein's concept of family resemblance, like what makes a game a game. There isn't one strict definition, but a network of overlapping similarities.
Exactly. Scientific education, particularly at higher levels, powerfully reinforces this. Students are trained through problem solving with exemplars. For instance, they learn to apply Newton's second law, F-ma, to various situations: free fall, simple pendulums, interacting harmonic oscillators. Each application requires a specific mathematical form, sure, but the student learns to see a variety of situations as like each other, even if the explicit rules or derivations aren't immediately apparent to them. They develop an intuition.
This idea of tacit knowledge is so powerful. It's like learning a skill, isn't it? Like riding a bike. You don't consciously follow explicit rules about balance and physics. You just learn to do it. Is this how scientists truly operate?
Absolutely. And it leads to what Kuhn calls specialization. I love his illustration of its impact. He asks, if you ask a distinguished physicist and an eminent chemist whether a single atom of helium is a molecule, they'll both answer without hesitation, but their answers will differ. For the chemist, yes, it's a molecule because it behaves like one kinetically in gases.
Right.
For the physicist, no, it's not because it shows no molecular spectrum.
Yeah.
Their answers are shaped by their disciplinary paradigms, even for the same basic entity. They literally see the same thing differently based on their training and what problems they typically solve.
Okay, here's the intriguing paradox Kuhn points out. Even though normal science is all about solving these predefined puzzles and even tends to suppress novelty, it's remarkably effective at stumbling upon entirely new and unexpected phenomena. These discoveries are often produced inadvertently, almost by accident, right? And they require the elaboration of another set of rules or concepts to make sense of them.
Right. Kuhn defines discovery as commencing with the awareness of anomaly. That moment, nature has somehow violated the paradigm-induced anticipation. It's not a single flash of insight, though. It's an extended, though not necessarily long, process of conceptual assimilation. It involves recognizing both that something is and what it is. It's a two-part process: noticing and understanding.
A famous example Kuhn uses is the discovery of oxygen. Joseph Priestley was arguably the first to isolate the gas back in 1774-75, but he interpreted it through the existing phlogiston theory, calling it dephlogisticated air, or even nitrous oxide sometimes. Lavoisier, a bit later, identified it as a distinct species. So Priestley found something, but he didn't really discover oxygen in the way Lavoisier did because he saw it through an old lens.
Exactly. Priestley, deeply committed to the phlogiston theory, was apparently never able to accept Lavoisier's interpretation of the gas. He couldn't see it that way. Lavoisier, conversely, was already prepared to discover the substance, partly because he had prior discontent with phlogiston theory. He was looking for something wrong. So the question, when was oxygen discovered, becomes impossible to answer precisely. Discovery isn't a single event. It's this complex process of both observing and conceptually assimilating something new within a new framework.
That makes sense. Another great example is the discovery of X-rays by Röntgen in 1895. This was a classic case of discovery through accident, wasn't it? Where Röntgen noticed a barium platinocyanide screen glowing unexpectedly near his cathode ray equipment. The crazy part is, another investigator had apparently seen that same glow and discovered nothing at all, just dismissed it as noise or something irrelevant.
This is key. While X-rays weren't explicitly prohibited by established theory, they violated deeply entrenched expectations implicit in laboratory procedures. People just weren't looking for them. And they meant that previously completed work on normal projects would now have to be done again because scientists hadn't recognized or controlled this entirely new, relevant variable. It fundamentally changed existing scientific fields, not just added a fact.
It wasn't just an addition, it was a disruption.
Exactly. And it also illustrates what Kuhn calls instrumental commitments. Priestley's use of a standard test for the goodness of air, how long a mouse lived in it, basically, implicitly committed him to the non-existence of gases that could behave as oxygen did, supporting combustion better than air. Similarly, the emergence of the Leyden jar, an early capacitor, involved overcoming prior assumptions about how electricity could be stored. Our tools and procedures shape what we expect, and therefore what we can easily see.
So summarizing the common characteristics of these fundamental discoveries, you have the previous awareness of anomaly, something not quite right, followed by the gradual and simultaneous emergence of both observational and conceptual recognition, seeing it and understanding what it is, and then the consequent change of paradigm categories and procedures, often accompanied by resistance. It's a real struggle, not a smooth transition.
Definitely a struggle. To drive this point home, Kuhn references the anomalous playing card experiment by Brunner and Postman. Fascinating study. Subjects were shown normal playing cards mixed with anomalous ones like a red six of spades or a black four of hearts. Initially, they'd simply see the red six of spades as a normal card, maybe misidentifying it as a red six of hearts or a black six of spades without any hesitation. Their brain just corrected it.
Wow, they literally didn't see what was there.
Not at first. As the exposure time increased, they'd start to hesitate, report feeling wrong, experiencing acute personal distress even. And then finally, sometimes quite suddenly, they'd adjust their conceptual categories to recognize the anomaly for what it was. That's a red six of spades. It's a powerful, almost literal metaphor for how novelty emerges in science. You have to break your existing categories.
And it suggests why normal science, despite not aiming for novelty and even tending to suppress it initially, is so effective in causing them to arise. Its extreme precision, its tight expectations, make it an incredibly sensitive indicator of anomaly, like a very finely tuned instrument that shows when something's off. The resistance to change also helps, ensuring that when anomalies do arise and persist, they penetrate existing knowledge to the core rather than being easily dismissed or explained away. It's like the paradigm's rigor creates its own potential undoing.
Well put. That rigor is key.
So these anomalies, when they persist and deepen, they don't just lead to new discoveries within the paradigm, they can also trigger a similar but more profound awareness of something fundamentally wrong, leading to what Kuhn calls a state of growing crisis in a field. And that crisis then paves the way for entirely new theories, not just discoveries.
Indeed. We see this pattern repeatedly throughout the history of science. Take the Copernican revolution, the old Ptolemaic system, Earth-centered. While initially successful, grew increasingly complex and inaccurate over centuries. It needed more and more elaborate patches, epicycles on epicycles. By the 16th century, astronomers like Domenico de Novara and Copernicus himself described it as a monster, a clear sign of a crisis state in astronomy. It just wasn't elegant anymore.
It became unwieldy.
Exactly. Or consider the chemical revolution in the 1770s. The phlogiston theory faced a crisis due to a couple of things. One was the rise of pneumatic chemistry, distinguishing different gases like CO2, which phlogiston struggled with. The other was the question of weight relations, specifically how metals gain weight upon burning. If phlogiston was leaving, shouldn't they lose weight?
A major contradiction.
Huge.
Yeah.
This led to a proliferation of versions of the phlogiston theory, desperate attempts to patch it up, which Kuhn says is a very common symptom of a paradigm in crisis.
Trying to plug the leaks.
Right. And then there's the crisis that preceded relativity theory. While early criticisms of Newton's absolute space by figures like Leibniz didn't have much impact experimentally, the later wave theory of light and the failed search for ether drift, most famously the Michelson-Morley experiment, eventually created a profound crisis for the mechanical paradigm. Even though Maxwell's electromagnetic theory had actually originated from within that paradigm, the implications, especially regarding light speed, just kept creating problems. The cracks just kept appearing.
So when a field hits this crisis point and things aren't adding up, my initial thought might be, okay, this theory is clearly broken, time to scrap it. But Kuhn suggests it's not that simple, does he? Do scientists just immediately throw out the old theory, or is it more complex?
It's much more complex. Not that simple at all. A crucial and often counterintuitive point Kuhn makes is that scientists do not renounce the paradigm that has led them into crisis easily. They only do so when an alternate candidate is available to take its place. The rejection of one paradigm is always simultaneously the decision to accept another.
You can't just reject something into a vacuum.
Exactly. It's not about simple falsification by direct comparison with nature alone. It's a comparative judgment between competing paradigms. You don't abandon the sinking ship until you see another one, hopefully a better one, you can jump onto.
But doesn't that risk scientific stagnation? If they're waiting for a perfect alternative, couldn't a field get stuck in a crisis for decades?
It absolutely can, and has. The Ptolemaic system endured for centuries while in crisis. But the pressure from anomalies, the growing awareness of problems, and the proliferation of those competing, often ad hoc, attempts to fix the old paradigm eventually makes a truly new solution highly attractive when it appears. And it's not every little anomaly that triggers a full-blown crisis either. They usually must be sufficiently fundamental or have particular practical importance, like astronomical predictions being way off for calendar design or navigation.
Okay, practicality matters. And when a new paradigm does finally emerge and take hold, it's a total transformation, isn't it? It's a reconstruction of the field from new fundamentals, changing both theoretical generalizations and paradigm methods. Kuhn likens it to picking up the other end of the stick.
Yes, or experiencing a change in visual gestalt like those optical illusions. Though unlike a simple optical illusion, scientists don't usually switch back and forth at will. Once they adopt the new way of seeing, they become deeply committed to it. It just makes more sense of the world to them.
What's interesting is that these new paradigms can sometimes emerge, at least in embryo, even before a crisis is widely recognized by the whole community. Lavoisier's sealed note on combustion, for instance, predated the full crisis in pneumatic chemistry, almost as if a few people are seeing the world differently before everyone else catches up.
That's right, foreshadowing the revolution. And during these extended crises, scientists often turn to philosophical analysis as a way of unlocking the riddles of their field. They start questioning the very foundations. Thought experiments, like the famous ones used by Galileo, Einstein, and Bohr, play a critical role in exposing the flaws of the old paradigm with a conceptual clarity that's sometimes hard to achieve in a messy laboratory.
Stepping back to think it through.
Exactly. And Kuhn also notes it's often men so young or so new to the crisis-ridden field who are less deeply committed to the old ways and are therefore more likely to propose these revolutionary shifts. They haven't invested decades in the old paradigm, haven't got the same ingrained habits of thought.
Less baggage, perhaps. Now, for perhaps the most radical and honestly mind-bending idea Kuhn presents. When paradigms change, he says, the world itself changes with them. He means that scientists see new and different things when looking with familiar instruments in places they have looked before. It's as if the professional community had been suddenly transported to another planet. How does he mean that? Is it just a metaphor or something deeper?
It's definitely more than just a metaphor. It's absolutely central to his argument. This is where those Gestalt experiments, the duck-rabbit illusion, the experiments with inverting lenses, or the anomalous playing cards we discussed earlier, serve as elementary prototypes. They're analogies for these larger scientific transformations. Kuhn suggests that something like a paradigm is prerequisite to perception itself. Our prior visual conceptual experience, our training, literally teaches us what and how to see.
So it's not just a reinterpretation of fixed neutral data. It's like the data itself appears differently. A pendulum is not a falling stone, nor is oxygen dephlogisticated air. The shift is a relatively sudden and unstructured event, like the Gestalt switch. Scientists often describe it with phrases like the scales falling from the eyes or a lightning flash that illuminates a previously obscure puzzle. It's a click.
Exactly. And we have powerful historical examples of these perceptual shifts. In the 17th century, guided by effluvium theories of electricity, electricians literally saw chaff particles rebound from electrified bodies. That's what their theory described. A modern observer with our paradigm of charges and fields would see electrostatic repulsion. Same phenomenon, different perception, different description.
Different world, in a sense.
In a very real sense. After Franklin's paradigm shift, the Leyden jar was seen as a condenser, its structure perceived differently. The two conducting coatings became prominent, rather than just seeing it as a special kind of jar. The object itself seemed to change in how it was perceived and understood. Lavoisier saw oxygen where Priestley had seen dephlogisticated air. And in doing so, he had to change his view of many other more familiar substances, perceiving compound ores where others saw elementary earths. It reconfigured his whole chemical world. And famously, Aristotle saw a swinging stone as a heavy body swinging back and forth, falling with difficulty, its motion inherently decaying. But Galileo, influenced by the impetus theory and later ideas, saw a pendulum.
A different object conceptually.
A completely different conceptual object. He saw something that almost succeeded in repeating the same motion over and over again, an ideal motion being hampered, not a natural decay. Galileo even saw regularities, like the period being independent of amplitude for small swings, which simply didn't exist conceptually for an Aristotelian observer, because for them it wasn't a pendulum striving for constant motion at all.
Even more provocatively, Kuhn argues that the numerical data of chemistry began to shift with paradigm changes. How could the actual numbers change? That sounds impossible. That feels really counterintuitive.
It's startling, yeah, but think about how measurements are interpreted and selected. Consider Dalton's atomic theory revolution. In the 18th century, affinity theory viewed solutions, like salt dissolved in water, as chemical compounds, which explained why they were homogeneous. Dalton, coming from meteorology, saw gas mixtures as a physical process where chemical affinity played no part. This made the observed homogeneity of the atmosphere a problem for him. Why does the heavier oxygen settle to the bottom? His paradigm framed the world and its problems differently.
Okay, so his starting point was different.
Totally different. And his assumption of simple whole number ratios for chemical combination, which came partly from his physical atomism, made the law of constant proportion a tautology for him. It was basically built into his definition of a pure chemical compound. Anything not in fixed proportion was ipso facto not a purely chemical process, but a mixture. This new system of chemical philosophy fundamentally changed how chemists practiced their science. It led them to look for and find new regularities and even obtain different concrete results in measurements, as chemists, in effect, beat nature into line with the new paradigm. They now knew what kind of results to expect and select as valid.
That's incredible. This also sheds light on what Kuhn calls the invisibility of revolutions. Textbooks, in their effort to quickly teach current knowledge, make the history of science look linear or cumulative. They often omit these revolutionary reorientations, like Dalton borrowing from physics. They might even misattribute concepts, like crediting Robert Boyle with the modern definition of element, when Boyle actually used the term but changed its significance within a new corpuscular context. It's like the past is constantly rewritten to make the present seem inevitable.
Exactly. Smoothing over the bumps. And this brings us to a really key concept for understanding why these shifts are so difficult. Incommensurability. That's the core reason why debates between proponents of different paradigms cannot be resolved by logic and experiment alone. Proponents of competing paradigms are at least slightly at cross purposes because their standards or their definitions of science are not the same. Even their language differs.
They're talking past each other.
Pretty much. Old terms like Earth for Copernicus, it became just another planet, or space for Einstein, no longer a passive container, take on entirely new meanings within the new paradigm. Kuhn says communication across the revolutionary divide is inevitably partial. It's like they're speaking different, though overlapping languages, even when using the same words.
And that's why conversion is so difficult. Charles Darwin wrote in Origin of Species that he didn't really expect to convince older, established naturalists. He said their minds were struck with a multitude of facts all viewed from a point of view directly opposite to mine. They couldn't just unlearn their perspective. Or Max Planck's famous, somewhat melancholic remark, a new scientific truth does not triumph by convincing its opponents, but rather because its opponents eventually die and a new generation grows up that is familiar with it.
It's a stark thought, isn't it?
It really is. It suggests it's less about a rational debate leading to consensus and more about waiting for the next generation to literally take the reins, a rather cynical, maybe, but perhaps realistic view of how progress truly happens sometimes.
It does highlight Kuhn's point that paradigm choice isn't purely logical. It's ultimately about persuasion, not proof, and can even involve personal and inarticulate aesthetic considerations, like preferring a theory because it seems simpler or more elegant. The crisis merely provides the crucial context, the opportunity for this shift, but the conversion itself is almost, well, personal, or at least communal.
So how do scientists even talk to each other across these divides if they're incommensurable?
Well, Kuhn suggests a practical approach, though it's not easy: becoming translators. Individuals on both sides can try to recognize each other as members of different language communities, and then attempt to understand how terms and concepts are used differently in the other paradigm. By leveraging shared everyday language or pointing to concrete examples, they can try to experience vicariously something of the merits and defects of each other's points of view. It's not about immediate agreement, but about achieving some level of mutual understanding first.
So translation aids persuasion, perhaps, but it's distinct from conversion. Conversion is more like that gestalt switch, a sudden slipping into the new language without a conscious decision having been made. You just see it differently. And those who are persuaded intellectually but cannot fully internalize the new view, they remain, as Kuhn puts it, a foreigner in a foreign environment. Able to use the new theory, perhaps, but never fully at home in its conceptual world. It's like learning to speak a language fluently without ever truly thinking in it.
That's a great way to put it. They haven't had the full aha moment.
So wrapping this up, what does this all mean? Kuhn's work on scientific revolutions leaves us with a really profound realization, doesn't it? Science isn't just about steadily adding facts to a grand edifice. It's a dynamic, occasionally jarring, and often beautiful revisioning of reality itself. It's about seeing the world anew, sometimes in ways that make the old world seem utterly unrecognizable.
Absolutely. And this framework offers a glimpse into why science seems to progress to solve problems in a way that other fields like art or philosophy often don't seem to, or at least not in the same cumulative way. Part of the answer lies in its unique social communities, in its very specific educational initiation, that systematic use of textbooks, and that intense emphasis on puzzle solving within a paradigm. That shared training creates both the stability of normal science and the conditions for eventual revolution.
So what does this all mean for you, listening right now? As you go about your day, maybe consider how your own worldview or paradigm, the unspoken assumptions and frameworks you've absorbed from your own experiences, your education, your communities, how does that shape what you perceive? What do you understand? And even what questions do you think are worth asking? This isn't just about science. It's about how any group or individual experiences reality.
Yeah, and maybe a final thought to leave you with. If our deepest knowledge is often tacit, embedded in how we are trained to perceive, and if different groups, trained differently, can truly live in different worlds based on their shared experiences and paradigms, then how much of what we call objective truth is actually a kind of time-tested and group-licensed way of seeing that we have assimilated? And what might we gain if we learn to be better translators of other ways of seeing, whether in science or politics or just everyday life?